Hello everyone, welcome to my talk. My name is He Qian and I'm assistant professor in the National University of Singapore. Today I'm going to talk about studying the compositions of individual alloy nanoparticles, also known as nanoalloys, using a correlative electron microscopy approach. Basically, we use a TEM to image the nanoparticles and measure their size, and then use a SEM to analyze the composition of the same individual nanoparticles. So we can plot nanoparticle composition against their size and get a composition distribution. Now, let me take you through why and how we're doing it, and what are the benefits and the challenges. Our research group has been mostly interested in the catalytic applications of nanoparticles. In a monometallic catalyst, the most important factor is the particle size, which will at least partially determine other effects such as the shape of the particle or the metal support interactions. Therefore, in most studies of practical catalysts, you will always find what we call a particle size distribution. Since we'll get a lot more interested when it comes to nanoalloys, because now you have an additional tuning knob of particle composition. This will bring out other effects such as electronic interactions among different metals, strain effects, and sometimes site isolation effects. However, unlike the previous case, most of the studies on nanoalloys only focus on analyzing individual nanoparticles, while the composition distribution among different particles, which for nanoalloys is at least as important as the particle size distribution, is rarely studied. I believe part of the reason is that such statistical analysis is not efficient and too time-consuming. Here I listed a few studies in literature where the composition distributions of nanoalloys were actually reported. Several common features can be observed. Firstly, in all cases, the composition of nanoparticles varies significantly from particle to particle, indicating the difficulties of controlling them during the synthesis and the necessity of this type of analysis. In addition, XEDS were mostly used because a lot of the catalytically important elements are rather heavy. I can only find one EOS study which is shown here. Thirdly, the electron energy used in these studies were either 200 to 300 keV or 100 keV with aberration corrector. This ensures high spatial resolution so that both imaging and analysis can be done in the same instrument. But this also means that the electron energy was not purposely optimized for chemical analysis, so that the efficiency of the analysis is rather low. Consequently, the number statistics were rather limited, and the quantifications come with large errors. The high beam energy also likely to induce knock-on damages, both to the particles and the support, which put another limit on the quality of the analysis. In this work, we want to optimize the efficiency of EDS analysis. So we separated the functions of high-resolution imaging and the chemical analysis into two different instruments. Nanoparticles will be first located and imaged using a 200 kV TEM. Then a 20 kV SEM equipped with a large EDS detector was used to do the analysis on the same particles. The benefits of using 20 kV electrons firstly come from a larger ionization cross-sections for the elements of interest. For instance, for the palladium L shell and gold M shell, the cross-sections will be 3 to 4 times higher compared to those for 200 kV electrons. Another benefit is that on conductive samples, relatively large beam current can be used for analysis, as we don't need to worry about knock-on damages. And the SEM geometry also permits the use of larger detectors. All in all, the efficiency of XEDS will be largely improved. We also argue that this setup could be more accessible compared to the state-of-the-art AC STEM instrument for doing routine statistical analysis of nanoalloys. In this slide, I show a comparison of typical results obtained from this correlative EM approach and the AC STEM. Within the same amount of time, a 20 kV SEM can give much more X-ray counts from a 6 nanometer gold palladium particle, although the AC STEM has much better spatial resolution. More counts means higher precision for composition of quantification. For instance, 10,000 counts will give about 1% counting uncertainties while it is 10% for the AC-STEM case. Also notice that in many cases, the particle is not even visible in the SEM, but it can still be analyzed if it is well isolated from other particles and has some recognizable features nearby. Here is a summary of gold-palladium nanoalloys studied using this correlative EM approach. These two samples were prepared with slightly different colloidal methods. And the only difference between the two was the different polymers stabilizers they use. Due to a higher analysis efficiency now, about 100 to 200 particles can be studied in each case within a few hours session. And this number is already close to what is usually needed for getting a good particle size distribution. This top row shows the individual particle compositions plotted against their sizes, with 99% confidence intervals also displayed, showcasing the measurement precisions. And the bottom row shows the average particle compositions at certain size range. The column plots underneath it are the particle size distributions, which are largely identical for the two samples. From this data, we can observe that there are large composition variations for small particles in both cases. In addition, the PVA sample appear to also have a systematic composition variations with particle size, as larger particles become more and more palladium-rich, which is not observed for the PVP sample. Seeing this effect is the first step towards understanding and eventually controlling them. This slide shows some practical considerations for using this correlative EM method to do nanoparticle composition analysis. As we briefly mentioned earlier, the targeted particles need to be relatively isolated. Some good examples are highlighted in yellow circles here, and those particles are at least 10–50 nanometers apart from the nearest neighbors. Secondly, if the particles getting too big, the beam broadening may introduce some artifacts, especially if the composition is not uniform within the particle. But for catalysts that we are studying, the particles are usually below 5 to 10 nanometer, and we won't have a huge problem with 20 keV electrons. Since the SEM usually have a lower vacuum compared to a STEM instrument, we were using a UV cleaner to handle the contamination problem. Just to make sure that the UV cleaner and the analysis process didn't induce any unwanted morphology change to the particles, we compared the TEM image before and after the analysis. As you can see, the particles remain largely unchanged as long as they are well separated. To summarize, in this short presentation, I hope I convinced you that analyzing composition distributions for nanoalloys is just as important and necessary as getting particle size distributions. We just need more efficient methods. And this correlative EM approach aims to do just that. And on this specific task, this approach is probably even better compared to using much more expensive aberration-corrected instruments. And as an example, we demonstrated that for gold-palladium nanoparticles, subtle differences in the particle synthesis process can have unexpected impact on the particle composition distributions. More information about this study can be found in the published manuscript. I would like to thank all the contributing authors from Cardiff, Lehigh, and NUS, especially the two students who did most of the groundwork, Shikai and Ella. I would like to also thank the good help from Hitachi and the Cardiff colleagues for instrument access. Thanks for your attention, and welcome any comments and questions you might have.